Okay, and the masked professor is on the air once more. Well, I hope you enjoyed yesterday's video. Well, actually you didn't enjoy yesterday's video because I accidentally erased it. And so today we're doing it again. How exciting for us. Anyway, I'm going to ditch the mask at this point, since I'm here alone, sitting in the dark, kind of creepy a little bit, but hopefully you'll be able to see the screen much better. Okay, so let us plunge boldly into today's lesson, which will be the beginning of Chapter 8 for our basic statistics and probability class. All right, now I feel as though some things have been left out of this presentation. So I am going to stop and work on showing you how some things work with this. Pardon me, I have to recover my tea that I left over by the camera. Okay, there we go, all teed up, so to speak. So I want to take it very slowly through this chapter because this kind of sets up everything that you're going to have to study in inferential statistics. So here we go. Yes, it's applied statistics and probability for engineers. All right, so we have the chapter outline that's of little value to us. All right, so Chapter 8 is about intervals. Confidence intervals is where we're going to start. And what we do with confidence intervals is we say we are pretty sure that some part of our distribution fits within, right? We can do confidence intervals on variance. We can do confidence intervals on standard deviation. In this case, though, we're going to start by talking about confidence intervals on the mean. So, a confidence interval estimate for mu is an interval of the form, the probability that L is less than or equal to mu is less than or equal to U equals 1 minus alpha. Okay, so you'll notice 1 minus alpha. And you may be saying to yourself, wait a minute, alpha, we never talked about alpha before. Alpha is a concept that we use in statistics. It is what we call a type 1 error. Type 1 error means that we are shading our estimate a little on what we think our statistics are going to be. So sometimes we'll talk about being 95% confident or 99% confident, or there are other intervals that we'll use. All right, and I'll go more into alpha later. I'm not just going to leave you with that short explanation and you're going, oh my God. All right, this is where the endpoints L and U are computed from our sample data. Okay, so we have a sample. We are going to estimate mu in this case, and we use our sample data to construct an interval that we say, yes, we're pretty sure it's in this interval. So there is a probability of selecting a sample for which the confidence interval will contain the true value of mu. Okay, again, by putting in mu, or putting in alpha, we are saying we're confident at the 95% level this is true, or the 99% level, etc. The endpoints, or the bounds, L and U, are called the lower confidence limit and the upper confidence limit, and it's called the confidence coefficient. Is it called the confidence coefficient? I'm not familiar with people using that language, but of course, people talk about things in different ways in different areas, so you know what? I'm just not going to worry about it. All right, now, this is about the confidence interval on the mean with the variance known. Now, everything we've done so far has been pretty much in the standard normal distribution. In that standard normal distribution, we assume always that we know the variance. We will start working with what's called the t-distribution, where the variance is not known, but we're not going to do that yet. So our confidence interval on the mean with the variance known, if x bar is the sample mean of a random sample of size n from a normal population with known variance sigma squared, a 100 times the quantity 1 minus alpha percent confidence interval on mu is given by x bar minus z alpha divided by 2 times the standard deviation divided by the square root of n less than or equal to mu less than or equal to x bar plus z alpha divided by 2 times the standard deviation divided by the square root of n, where z alpha divided by 2 is the upper 100 times alpha divided by 2 percentage point of the standard normal distribution. All right. Before we go any further, let's start talking about alpha. What is alpha? Alpha is a probability that we are working with, right? We are working with alpha, and alpha is the probability that we say we might be wrong in our approach. Okay? So how do we find alpha, and how do we find Z alpha divided by 2? Both excellent questions. And so let's work through a couple of problems about how that is done. All right, so I'm switching over to the view, the Q view. The Q view. All right. And I am using an old book. Damn it, got to get a new Sharpie. Give me a second. Just like a real class, isn't it? I say just like a real class because as those of you who are my students know, I very often have forgotten something and have to go to my office, which is right behind here, and dig around and get it during class. And for those of you who don't know, well, it doesn't matter. You're not taking my class. All right. This problem is from our book, but the 5th edition of the book that we're using for this class. This is problem 8-2A. What value of Z alpha divided by 2 gives 98% confidence? Okay, my E looks terrible. Here, let's try that again. All right. All right, so how do we figure out what our Z alpha divided by 2 should be to get 98% confidence? All right, so we have to start with our confidence level percentage is going to be equal to 100 times the quantity 1 minus alpha, right? And of course that will be a percentage as well. All right, so we have established that. Now remember when I said that alpha is a probability. In this case, it's our probability of being wrong. All right, so our confidence interval percentage is the same as 98% that we have here. All right, so I'm going to substitute that into the equation. 98% equals 100 times the quantity 1 minus alpha percent. Now, I am going to go ahead and say, we know that in an equation, anything we do to one side, we have to do to the other, right? Equation derived from the same root as equal. All right, so I am going to now divide both sides by 100%. So when I do that, over here, I get 0.98, right? Dividing by 100 means I move the decimal place over 2 spaces as equal to 1 minus alpha. All right, so there you go. I've got that. Now, I am going to go ahead and subtract 1 from both sides. So 0.98 minus 1 equals 1 minus alpha minus 1. All right, so that is going to give me a 0.02 negative on the left side, and my ones will cancel out so that I have a negative alpha on the other side. Now, I don't want a negative alpha, so I multiply both sides by -1. Right, so that brings it down to be 0.02 equals alpha. However, I want Z alpha divided by 2. So, I divide both sides by 2, and that's going to give me 2 divided by 2, so it's 0.01 equals alpha divided by 2. All right, so now, I forgot to sequester a couple of pieces of paper here. Okay, paper sequestered. All right, so that 0.01 is a probability that is equal to alpha divided by 2. So I take my table and I take my standard normal distribution table, or Z table as we sometimes call it, and I am going to go hunting for 0.01 probability. All right, so I take the one paper and I say 0.01. There we go. Now, on this row, it looks like it's starting with 0.011011. But it looks like I should actually be on the row above. Okay, so I'm going to go ahead and do that. Then I'm going to look and I'm going to say, all right, what is the number, the probability on my chart here that is the closest one to 0.01? All right, well, I've got two really good candidates right here. 0.009903 and 0.010170. All right, so I am going to choose 0.010170. Why? Because that 170 means that it is 170 ten-thousandths away from 0.01, where this one is 197 thousandths, ten-thousandths away from 0.01. All right, so this is the one. And I come over here and I put down another piece of paper so that right here in the corner is my number. Using these two pieces of paper makes it super simple to make sure that you're using the right probability. Now, how am I going to read this? I am going to come over here and I'm going to say negative 2.3 plus negative 0.02. All right, so I add those together, it becomes a negative 2.32. Now, our z alpha divided by 2 is actually going to be on both sides. So let me illustrate that. All right, so I take away my pieces of paper. All right, there we go. Now, here is my standard normal curve. Please pardon me, it's not the best drawing ever. But I don't have time to break out the drawing board and all my little drawing tools and all that. Y'all would be very bored watching me do that anyway. Right in the middle, we know is mu. What we are doing is we are saying we know that alpha divided by 2 is 0.01 on our left side of the standard normal distribution, and it is also 0.01. Uh-oh, too many zeros. On the right-hand side. Okay? We know that mu is in the middle, right? And we're going to build our confidence interval around the idea that we know it's in the middle. We're going to exclude the far extremes of our standard normal distribution. All right, so we know as a consequence that our negative z alpha divided by 2 equals negative 2.32, and our positive z alpha divided by 2 equals 2.32. Okay, sorry, a little messy on my writing there. All right. Therefore, we are saying that our z alpha divided by 2 is equal to 2.32. Okay, nothing super fancy. We have to look at the table and extract some inference after we do the math to get here. All right, but look, this math is simple enough that once you get used to it, you should be able to do this without having to even write it down. And I know I can hardly wait for that. All right. All right, so let's just work that same problem with some other numbers. All right, so we'll go to problem 8-2B. And they ask, what is z alpha divided by 2 when we have 80% confidence? An excellent question. All right, so once again, we're going to take our basic equation for figuring this out, that our confidence interval percentage is equal to 100 times the quantity 1 minus alpha percent. We are going to substitute our 80% confidence number into that equation. So 80% equals 100 times the quantity 1 minus alpha percent. Okay, so when you have if you remember from algebra, and I'm sure you do, we've got one unknown and one equation. We can always solve a problem of that form. If we have two unknowns, we have to have two equations, three unknowns, three equations, and so on. Just don't ask me to solve for 47 unknowns with 47 equations. Oy vey, that would be a lot of work. All right, so there we go. We've got our equation, and we've got one unknown. I am going to divide both sides through by 100%. All right, so that means that these guys become 1, these guys drop out, this drops out, and we have 80 divided by 100. I could simplify it to 8 divided by 10, but it would be pointless. So that becomes 0.80 equals 1 minus alpha. Once again, I'm just going to go ahead and subtract 1 from both sides. That makes this 0.20 equals, a negative 0.20 equals a negative alpha. Once again, I can take this and I can say, you know what, I'm just going to multiply through by a negative 1, and that will take away my negative signs. So now I've got 0.20 equals alpha. Now I'm going to go ahead and divide through by 2. When I do that, on this side, obviously I'm going to get 0.10 equals alpha divided by 2. Okay, it's table time. All right, let me go ahead and say, I'll make my little normal curve illustration here. All right, so that means we're looking for where alpha divided by 2 equals 0.10 on this side. Our negative alpha divided by 2. And our alpha divided by 2, actually, leave it as positive, is also 0.10 probability on this side. So we got these probabilities on each end of the standard normal curve that we are excluding from our confidence interval. We want to know what is our negative z alpha divided by 2, and as a result, we'll be able to just remove the negative sign to get our positive c alpha divided by 2. All right, now I swear it's table time. Oh, it's table time. Oh, it's table time. All right, got to get my table up high enough that our numbers of interest are going to be in there. All right, so when I look at my table here, I am going to be looking for 0.10. All right, so it looks like right here is the place to go. And then I'm going to look at what is the best value. Okay, 0.100273, 0.102042. This one is much closer. Is it closer than this one, 0.98525? Yes, it's only 273 10,000ths as opposed to, what would this be? 1,475 thousandths. All right, so it's this number right here is our best choice. And I just go ahead and put my other piece of paper so that I have my my probability here defined the best way possible, and I can get my numbers, right? So I look here, it's negative 1.2. I look up on the top, and it's negative 0.08. I add those together to get a negative 1.28. So that means that Z alpha divided by 2 is 1.8. All right, having said that, I then transfer that knowledge and say that Z alpha divided by 2 equals 1.28. Now this goes along with what I often have told you. Statistics is somewhat complicated, but it's not necessarily hard. You have to know where are you now, what information you've got, and what we're going after, and we can solve our problems every time. Of course, easy for me to say, this is like the 25th or 26th or even 27th time I've taught statistics. All right, so let's go back up to the top, and we'll do one more of of our examples from problem 8-2. Again, we want to know what is our Z alpha divided by 2, and our confidence level is equal, in this case, to a 99% confidence interval. All right, so we say we know our confidence interval percentage is equal to 100 times the quantity 1 minus alpha percent. We know that 99% is our confidence level for our interval. So I'm going to substitute that in over here. All right, so 99% equals 100 times 1 minus alpha percent. Once again, I am going to divide by 100%. Okay, so when I do that, I divide 100 into 99. That means I move my decimal place over 2 places. 0.99 equals 100 divided by 100 is 1. Percent divided by percent means we throw that away. So 0.99 equals 1 minus alpha. All right, so once again, we just take our 0.99 minus 1 equals 1 minus alpha minus 1. All right, so that means my 1's drop out. On this side, it becomes negative 0.01 equals negative alpha. I multiply through by negative 1, and I get 0.01 equals alpha. I am then going to divide both sides by 2, right? Because we're looking for z of alpha divided by 2. That means that over here, I'm going to get 0.005 equals alpha divided by 2. Now, once again, because, got to come down a little. Because we're working in the normal distribution, that means I am going to exclude this 0.005 probability, and I'm going to exclude this 0.005 probability. All right, so that's not too bad. Now, what we're going to look for is our negative z alpha divided by 2, which is right where this line is in our schema. And of course, on the other side, we have z alpha divided by 2. But if I were going to look at that, I'd have to do 1 minus 0.005. Oy, boyjama. I would only do that if I have one of those silly one-sided z tables. All right, so I take my z table, right? You can see I've got my z table here. Now I'm going to look and I'm going to say 0.001. No, that's not what we want. We want 0.005. And it looks like this is the line for it, right? We got some 0.005s here. It looks to me like the two probabilities that are the closest to our alpha divided by 2 are this one, 0.004940, and this one are 0.005085. Okay, I would not get horribly upset if you chose either one of those, but this one is only 60 100,000ths away from the number we want, whereas this one is 85 100,000ths away from the one we really want. So I choose the one that is 60 away. Okay, so our number then we're going to find by following over to here, negative 2.5, and following up to here at a negative 0.08. Okay, that being the case, we're going to add those together and get negative 2.58. So that means our negative z alpha divided by 2 equals negative 2.58, and our positive z alpha divided by 2 equals 2.58. All right, just to make sure that you understand, let's go ahead and say 1 minus alpha divided by 2 equals 1 minus 0.005. That is going to be equal to 0.995. In this case, I am going to take my positive table positive z numbers, that is. Probability is always a positive sum. All right, here is the line that starts with the 0.995. But I notice I have to go up to get closer to the correct values. All right, so it's at 2.5, the same as when we were looking at the negative z alpha divided by 2. But in this case, we're looking for the positive z alpha divided by 2. And I'm coming over here, and I'm getting closer and closer and closer, and it looks like right here is where is going to be the closest, right? This one is 85 100,000ths away, and this one is only 60 100,000ths away. Where have I heard that before? All right, so I put down my other piece of paper. Right, so I make it very easy to find my numbers. And I'm going to go up 2.5 plus 0.08. What a surprise that that is how it came out. No, I'm lying. Of course it's not a surprise. I predicted to you that our negative Z alpha divided by 2 number would be equal to our positive Z alpha divided by 2, except multiplied by negative 1. So there, take that. I want to do a couple more problems, but I want to approach it from a slightly different standpoint. So now we're going to do problems that are in 8-1 in the old 5th edition textbook. What is the confidence level for the interval x bar minus 2.14 times standard deviation divided by square root of n less than or equal to mu less than or equal to x bar minus plus 2.14 times standard deviation divided by the square root of n. All right, so this is exactly like the problems that we've been solving, but a little bit inside out. So we can see that negative Z alpha divided by 2 equals negative 2.14. Right? And conversely, our positive Z alpha divided by 2 equals 2.14. All right, we're going to use exactly the same ideas that we were using before. Please pardon my handwriting. I seem to have injured my wrist, and I can't write well because I'm left-handed, and of course I injured my left wrist. All right, so I am going to put this where I know my my negative 2.1 row is. All right, so I'm coming over here and putting that down. Right, so that's my negative 2.1, and it just goes down that row. Then I'm going to look and I'm going to say, you know what, this is the negative 0.04. Because we know to get that negative 0.14, we have to add this number and this number, right? So I just take another piece of paper, and now I have exactly my probability that is equal to alpha divided by 2, right? So that is 0.016177. Well, you know what? It sounds like a lot of work to use that extra 177. I'm going to throw that away. I'm going to call it 0.016. All right, so alpha divided by 2 equals 0.016. Now, I need to get alpha. So I am just going to multiply both sides by 2, right? That means that my 2's turn out to be a 1 on this side, and I have alpha. And on this side, it's going to become 0.032. Now, I'm looking for the confidence level. All right, so confidence level equals 100 times 1 minus alpha percent. I don't know about you, but it sounds like we're almost finished with this problem. All right, so I substitute in my alpha. 100 times the quantity, 1 minus 0.032%. That's going to come down to 100. 1 minus 0.032 is going to be 0. Let's see, it would be 97, but it's actually going to be 0, excuse me, is going to be 968. When we multiply something by 100, that means we're going to move our decimal point over 2 places. So here and then here. So we put down 96.8% is our confidence level. Well, wasn't that fun? What? I'm not hearing a rousing yes. Well, of course not. I'm here all by myself. So, that was actually 8-1A. Now I am going to go ahead and do problem 8-2b. Okay, what is the confidence level for the interval x bar minus 2.49 times standard deviation divided by square root of n, less than or equal to mu, less than or equal to x bar plus z alpha divided by 2 times standard deviation divided by the square root of n. Okay, boy, my handwriting's getting worse and worse. All right, easy enough. Now, we are going to go ahead and work this the same way that we did before. So our negative z alpha divided by 2 equals negative 2.49. Oh, this should have been 2.492, but but I spaced on that. Doesn't matter. We're going to go after the negative one as the easy one to get. All right, so that means we want to know what our alpha divided by 2 is. Luckily, I've got a table. All right, so I put my table down, and there we go. All right, so I look for negative 2.4 and then I'm going to look for negative 0.09. All right, so where those add up, negative 2.4 and negative 0.09 comes together at 0.006387. All right, so that is our alpha divided by 2. Now, once again, to avoid having to go through a lot of tedious math, I'm going to throw away those last 3 numbers and just take it as 0.006. So alpha divided by 2 is 0.006. That means that if we multiply both sides by 2, we are going to get alpha is equal to 0.012. From there, I'm going to go back to my old-fashioned confidence interval formula. Confidence interval percentage equals 100 times 1 minus alpha, that quantity percentage. All right, so 100 times the quantity 1 minus alpha, and that's going to be a percentage. So, next I'm going to say 100 times the quantity 1 minus 0.012%. That's going to be equal to 100 times 0.988. We would move our decimal place over twice when we multiply by 100. So it becomes 98.8% is our confidence level. All right, so holy tuxedos, we've done a lot of problems about how do we find our alpha divided by 2, or going the other way, find our confidence level when we know the z number associated with our alpha divided by 2. All right, so over here, back at the slideshow, right? Now you remember our confidence interval, when we know the variance, is calculated as x bar minus z alpha divided by 2 times standard deviation divided by the square root of n less than or equal to mu less than or equal to x bar plus z alpha divided by 2 times the standard deviation times n. Surprisingly enough, they have an example here. Example 8.1. We have 10 measurements. So what does that mean? That means n is equal to 10 of impact energy in joules on specimens of A238 steel cut at 60 degrees centigrade are as follows, and they're 64.1, 64.7, 64.5, 64.6, 64.5, 64.3, 64.6, 64.8, 64.2, and 64.3. Oy vey. The impact energy is normally distributed with the standard deviation being equal to 1 joule. We want to find a 95% confidence interval for mu, which is the mean impact energy. All right, so these guys, of course, in the examples in the slideshow, they take a lot of shortcuts that I wouldn't take. So z alpha divided by 2 equals z of 0.025 equals 1.96. If you don't believe them, you can feel free to go through and work that in the manner that I showed you. N equals 10 measurements. Standard deviation equals 1, and X bar equals 64.64. I've already calculated that. Yes, it's right. So our resulting 95% confidence interval is found from equation 8-1, X bar minus Z alpha divided by 2 times standard deviation divided by square root of n less than or equal to mu less than or equal to X bar plus Z alpha divided by 2 times standard deviation divided by square root of n. We substitute in those numbers. All right, so 64.64 minus 1.96 times 1 divided by square root of 10 less than or equal to mu less than or equal to 64.46 plus 1.96 times 1 divided by square root of 10 gives us, finally, a confidence interval of 63.84 less than or equal to mu less than or equal to 65.08. All right, so now we are 95% confident that our mean impact energy is between 63.84 and 65.08. And those, of course, are in joules. Now, this could have been done at any confidence level. We could have done it at the 99% confidence level, the 90% confidence level. We could have done it at this 10% confidence level, but usually that's not done. All right, so what I would like to do is all right, so we have a bunch of data sets here from the publisher. All right, and what we're going to do is we are going to work through to get a confidence interval on a couple of them. All right, so I'm just going to start with the very first one. I'm going to copy my values. And put those here. I'm going to go ahead and copy this so that I can, first of all, rename the sheet, and second of all, I'm going to mark this as example 8.1.6. All right, so these are my XI values. Oh, wait, I need to make this a lot bigger. What the hell, make it even bigger. All right. Now, I want to find a couple of things. One is I want to find what is our sample mean, or our X bar. All right, so we're going to say equals X bar. Oh, right, I forgot. You have to put a single quote in front of equals when you use that in Excel if you're not actually doing an equation. All right, you all know how to do this, or I'm praying that you learned how to do it. We put equals average. We highlight our numbers. We put a right parenthesis. Okay, so our average is 90.48. All right, well, that's easy enough. Now, we do have a problem. We don't have our variance, and as a result, we don't have our standard deviation. Okay, so I am going to pretend that my sample standard deviation is the same kind, is my standard deviation. And don't forget the single quote here. All right, now I've got to the part where I need to put in the equation, because if I just write it out like I would if I were just working with myself, then it might confuse y'all. Okay, so this is X bar minus Z, alpha divided by 2, go up here for Greek letters, alpha divided by 2, that is times a fraction, our standard deviation divided by the square root of n, I really love creating equations like this. All right, so less than or equal. Got to go back to Greek letters for mu. Mu, where's mu? Ah, there you go. I really should have memorized my Greek letters in order, but I'm too lazy. All right, now, this part of the equation over here, right over here, it's X bar minus Z alpha divided by 2 times standard deviation divided by square root of n. On this side, the only difference is it's going to be plus Z alpha divided by 2. So I'm going to just copy, paste, and change my minus to a plus sign. All right, now, what am I missing over here? I need my sample size, right? So I'm going to say this is equal to count. Just highlight my numbers. Obviously, in this case, how hard would it be to just count it by hand, right? But I want to teach y'all what to do if you have a really large data set, because that is going to happen to you sooner or later. All right, so here I'm going to put in my left side of the equation. And that is that it is equal to x bar. Now, z alpha divided by 2, we didn't really discuss that, but it's very common to use the 95% confidence level. In that case, what we would do is say minus 1.96, right? Remember that from the last example problem, times standard deviation divided by square root of n is less than or equal to mu less than or equal, and then we calculate our upper confidence level. All right, so that's equal to x bar plus 1.96 times our standard deviation divided by the square root of n. Bloody hell, been talking a long time. No, not very much lubrication. All right, so we have calculated the lower confidence level and the upper confidence level of the mean for this problem. Now, one thing to keep in mind, our mean here is only based on 5 numbers. There are circumstances in which that is a perfectly viable way of doing things, but it has what we call low statistical power. All right, well, I am going to call class, call it a day for class here, and I am going to post this video for you. I will post the problems in Moodle, and I will do what? I'll have another lecture for you later in the week. Thank you very much, and have fun. Bye now.